All right, we are now ready to define the hyperbola, and it's going to look almost identical to the ellipse. There's one key part in here we'll see. The hyperbola is a set of points in a plane in which the distance from a point P, or point xy, in the set to a fixed point, a focus, minus, that's the one difference between the ellipse and the hyperbola, minus the distance from that same point P, xy, to another fixed point, again, another focus, is constant. So this time, d1 plus d2, not plus, minus d1 minus d2 is some constant. And again, we'll define bits and pieces of this where that constant as well equals 2a. And so we've got very, very similar setup to the ellipse. Okay, as we look at some points here, we got two foci, again, not focuses, but foci, and just pick a point here that will eventually end up on our hyperbola. So d1 minus d2 will be this constant, and pick another point. We'll pick one right on the major axis, as we'll call this as well. d3 minus d4 will be that same constant. So the difference between the distances will equal the same number. And now here I pick this point right here. Notice that is not halfway in between the foci. We will still deal with a point halfway in between the foci as the center. We'll still call the center HK. And we'll call, we tend to use C a little too often. We'll call point C the center, HK. Now here we're using capital C as our constant, but that's going to be some other value here in a second. And once again, let's see, actually, yeah, once again we're going to call little c, you can tell that's a lot littler than these other c's, okay. Lowercase c is going to be the distance between the center to the focus, just like the ellipse, okay. Now, the major difference here is when we talk about the vertex or the vertices. The ellipse had two vertices. The hyperbola will also have two vertices. But those vertices will be inside the foci. So if we look at our major axis here, this is the foci will be on the outside. This will be vertex 1 and this will be vertex 2 with our center HK. And again, the distance of the major axis will be 2a. So the distance between the center and a vertex will be a, just like we defined the ellipse. The only difference is the foci are outside of the vertices on the hyperbolas. So what we're looking at here, if we want to kind of get a picture of the ellipse or the hyperbola, now this is probably most definitely not going to be close to scale, But if you measured all of these points and D1 minus D2 and all that, probably we're not going to get a constant on these differences, but we should. You'll just have to kind of imagine, just like you do with any of my drawings, imagine what they're supposed to be, not what they are. This would be the first focus. This would be the first vertex, center, second vertex, and then second focus. Okay, and then again, some point P, X, Y, where the definition fits. So we'll again set up our equation. And, well, we could even say this, D1 to D2, the difference, this constant, we probably should say the absolute value of this difference equals a constant. That difference could be a positive or a negative value. Depends on which one we define as D1 and D2. With this setup here, we'll actually end up with a negative value. But it's going to be the negative of the same absolute value. But what we have to think about as we set up the equation, and again, I'll wave my magic wand so we won't have to go through all that, but we'll still set up the equation. The focus F1, that coordinate is what? Once again, H minus C, and this is capital C right here, the center, which is our HK. Once again, with the horizontal major axis, the Y value remains K. The only thing that changes from focus to focus is the X value. F2 would be H plus C and K. So again, our basic equation, when we plug in these points, our distance 1, x minus the quantity h minus c squared plus y minus k quantity squared. That's a minus. Then minus d2 and that would be x minus h plus c quantity squared plus y minus k quantity squared, and again equals some constant, and I'm going to put plus or minus 2a. A again would be from the, like I've shown, from the center to a vertex. So plus or minus 2a depends on which distance we're starting with and which one we're subtracting. Okay. The plus or minus will go away because algebraically, to get rid of your square roots, we got to square both sides. Squaring positive or negative, that'll turn into the same value. So from here, again, pull out my magic wand, and top of the next page we'll see what the standard equation for the hyperbola looks like. So this is the equation we would get. Now, again, the horizontal major axis, we have not shown the relationship between A, B, and C. It will be different this time. But first, let's see what the vertical major axis looks like for the equation. So our vertical major axis, we have the y minus k quantity squared over a squared minus the x minus h quantity squared over b squared equals 1. Now the relationship here between a, b, and c is different than what we saw with the ellipse. The ellipse, a was bigger than c, but on the hyperbola, remember, c is going to be that distance. So the relationship between a, b, and c squared is going to equal a squared plus b squared. Whereas with the ellipse, it's a squared is going to equal b squared plus c squared. And another, I guess you could call it a major problem here, a is not necessarily bigger than b. Okay? The only thing we know for sure is that c is bigger than both a and b. Now, as we work through some examples here, finding equations of a hyperbola given certain information, we'll talk more details about this and how we would graph using the A and B and C. But at this point, we have all of the standard equations for the parabola, ellipse, and hyperbola. And tomorrow we'll go over some examples.